talk about string tension between de Sitter vacua and curvature corrections. And you know already what the rules are.
Yes, thanks. Okay, let me check that it works. Yes, okay, good. Okay, so good afternoon to everyone, and thanks Roberto for the introduction. Let me quickly start the talk by thanking the organizers for organizing this nice workshop, and also to for inviting me to give a talk. So in this talk, I will discuss the results of two papers in collaboration with Ivano Basile, another postdoc who is based at University of Mons. And it is about de Sitter existence of non-perturbative de Sitter solutions and their compatibility with higher derivatives corrections in string theory. Okay, so let me start with what the observations tell us. Observations tell us that our universe is currently undergoing a phase of accelerated expansion. And this could be explained in principle by many possible ways. Probably one of the most conservative and easiest solutions is to assume that there is a positive cosmological constant, but in principle there might be other solutions involving the presence of other fields, so quintessence, phantom energy, alternative models, and so on. Since the cosmological constant, the positive cosmological constant is at the moment one of the simplest solutions, and since observationally speaking, it is really difficult to distinguish between a constant cosmological constant, positive cosmological constant, and the quintessence, for instance, then a question naturally arises of whether this is compatible at all with quantum theories of gravity. And this is in particular a big deal in the context of string theory because of some of the swampland conjectures, since some of them imply that there might not be actually de Sitter solutions compatible with quantum gravity. But there are still, this is a conjecture, there are computations around, and seems like they are compatible with this conjecture. But so far, the computations that have been done are mostly within perturbative computations. And to the first few orders in the so-called alpha prime expansions. So it seems like there would not be there would not be de Sitter solutions within these calculations. But this does not exclude that de Sitter solutions could arise as a non-perturbative effect. So as the result of all higher derivative corrections, for instance, the so-called alpha prime corrections in the context of string theory. So this is a really interesting question to pose. But in order to answer this question, I mean, yes, it's possible in principle, but it's really, really hard, at least using standard techniques. And the idea of this work was to try to see if there is any out-of-the-box method, any out-of-the-box thinking that could allow us to derive all order solutions, at least on cosmological backgrounds, and make some steps, some first steps to investigate the existence of de Sitter solutions at a non-perturbative level. So, assuming that not everyone is familiar with the topic, I will very quickly recap some very basic facts. So, string theory arises essentially from the quantization of the Polyakov action, where there appears this very important parameter alpha prime, that is the inverse of the string tension, and is essentially the only free parameter in string theory. The classic collection, in principle, has diffeomorphism invariance and Weyl invariance, but this could be, in principle, broken at a quantum level because of the trace anomaly. And now, since Weyl invariance is really important in this context, one might want to really force the theory to be Weyl invariant by imposing this Weyl anomaly cancellation. And there are several levels, at least at which one can impose these conditions. And in particular, on flat spacetimes, this gives the famous constraints on the dimension of the spacetime, which depends on whether it can be 10 or 26, depending on whether one has a supersymmetry, is in a supersymmetric setting or not. Or on curved spacetime, there are even there several levels to first order in an expansion in this alpha prime parameter, one gets the Einstein equations. But in principle, if one has a non-zero space-time curvature, one would have infinitely many corrections to Einstein equations with infinitely many derivatives. And these are the alpha prime corrections. And if one is able to resum all of these, one would have an all-order result, at least within this alpha prime expansion. And in addition to that, these infinitely many corrections are constrained quite a lot by T-duality. Okay, the idea would be, in principle, it would be nice to resum all of these alpha prime corrections, but it is not easy in general, at least on general backgrounds. It is possible in some special backgrounds, for instance, these linear dilaton, and also in supersymmetric settings. But on cosmological backgrounds, it might be more involved. Still, on cosmological backgrounds, there are really remarkable constraints that come from T-duality, and in particular, by joining all of these conditions, so Weyl anomaly cancellation, integrating all massive modes, limiting ourselves to cosmological backgrounds and imposing the T-duality, one gets strong constraints on the cosmological effective action in the string theory that have been derived in this paper by Meissner and other papers by Hom and Zuibach. And it seems that under certain assumptions, so namely within mini superspace approximation within bosonic string and including no string loops corrections, the cosmological Lagrangian has this very simple form. So there is the standard term with the dilaton field plus some corrections that are written as an expansion in h square. H here is just the Hubble constant. So it is really all of these, all of the alpha prime corrections are given by an even function of the Hubble parameter, of the Hubble constant. And now the key point is that if one is able to compute all of these coefficients Ci and possibly resumming all of them, one would immediately not straightforward, but one would have access in principle to non-perturbative de Sitter solutions, so to possible exploration of the existence of de Sitter solutions at a non-perturbative level. But the problem of this is that the computation of these C coefficients via standard techniques employed in the context of string theory, so mostly based on scattering amplitudes, is extremely hard. And only the first few coefficients are known, and only on special dimensions. So this is the starting point. So it would be nice, of course, to access non-perturbative de Sitter solutions by computing and resumming all alpha prime corrections, at least on cosmological backgrounds. But it is very hard using standard methods. But now the point is, my collaborator and I realized that this might be actually doable using functional normalization group methods. And let me speak a little bit about these methods. So what these methods are about, so they are functional techniques based on this equation. This is a functional integral differential equations for this functional an effective action that depends on a normalization group scale, and the flow of this action is given by the variation of a regulator that is inserted by hand in the effective action in order to generate the flow, and the inverse full inverse propagator. And this equation, if one is able to solve it for the effective action, generates a flow that is typically thought as a flow from the UV from some fixed point action towards the IR. And if one is able to compute this flow for a given ansatz for the effective action that is practically given by its symmetries, then one would recover at k equal to 0 exactly the effective action with all corrections. And this equation has been employed in several contexts in asymptotic safety to check non-perturbative renormalizability in terms of the existence of ultraviolet fixed point, but also in condensed matter physics and QCT. In the context of string theory, it is not really necessary to have a UV fixed point for related to UV completeness or normalizability, because at much higher scale, it's believed that string theory should be renormalizable and have nice properties. So that is not the point. But still, this equation can be used as a tool to extract the effective action and to resum all alpha prime corrections. And to this end, it is important to have a fixed point as a tool, just because a fixed point comes with a finite number of relevant directions, possibly. And if one then follows the flow from the UV towards the IR, essentially one gets an effective action that has infinitely many corrections, but they are only parameterized by a few free parameters. And now the game is just to combine the symmetries and dualities of string theory with this equation in order to derive on a mini superspace all order alpha prime corrections, and make some step trying to understand whether there might be some de Sitter solutions compatible with string theory at a non-perturbative level. So one needs an ansatz that one has to replace into the functional normalization group equations, and the ansatz is inspired by the action that I have shown you a couple of slides ago, that was proposed by Meissner, Hom, and Zwieback. So there is again the dilaton term, the image dilaton kinetic term, and a function, an even function of h square, that is exactly what I've shown you here. Here there is an expansion in h square that contains all alpha prime corrections. And what I'm doing here for convenience, not to compute infinitely many beta functions, is to use a function of an even function of h square and compute the flow for this function. And this, if I can compute the flow for that, would give me all alpha prime corrections. So one can just take this guy, insert it in the functional normalization group equations, extract the beta functions, and hope to get some solutions out of that. This is quite more easier than standard perturbative techniques, but not very straightforward, in the sense that once one gets the beta functions, one notates something like this, so they are not lengthy. but they are still involved. They are non-linear, non-constantly delayed partial differential equations. So finding exact solutions is hard. Even numerically, the codes tend to be unstable. But we were able to find 2 solutions. In particular, one has to note that these equations are non-linear, so there might be multiple solutions. Okay, so first solution that we found is actually an exact solution in an arbitrary number of dimension. Here, the small d is the number of spatial dimension. And here I'm writing exact, but I mean, still it is exact in the sense that it is an exact solution to the beta functions that are computed, however, within the mini superspace approximation. So there are still the validity assumptions that I have shown you at the beginning. However, it is non-analytic. So the f function resembling all alpha prime corrections has this square root of h square. So it is non-analytic in h square. And of course, we don't like that, because while it is an exact solution, so this essentially would translate at the level of the effective action as a square root of r of the Ricci square of the Ricci scalar, and so this guy would essentially never give us Einstein gravity at any scale. Plus, it is non-analytic, so in principle, it is not really compatible with the initial expansion that I have shown you. But it is also interesting to see that the running of the equivalent of the dimensionless Newton coupling is given by this equation. So this is just the plot of the dimension-full counterpart of the Newton k-dependent Newton coupling. And just as an interesting remark, so this is exactly the same running that was found in a paper by Alfio Borando and Martin Reuter from the end of the 90s in the context of asymptotic safety, asymptotically safe gravity, using the Einstein-Hilbert approximation and the no cosmological constant. And this might eventually suggest a scenario like the one that has been proposed recently, that asymptotic safety, asymptotically safe gravity could realize itself as effective asymptotic safety, that in the sense that it is just an intermediate step towards a much more complicated flow towards a fully non-perturbative and stringy regime. Okay, and this is one of the solutions, but we don't like it. This is not compatible with Einstein gravity, and it is not non-analytic. So we wanted to understand whether there are more solutions, in particular analytic solutions, since this is our starting requirement as assumptions. And it was not easy to extract other analytic exact solution to the beta functions that we have computed. And so we have looked for an analytic solution employing an expansion about 2 dimension, an epsilon expansion about 2 space-time dimension, and we have computed the flow to leading order in this epsilon expansion. It was possible to follow the flow. So in particular, there is a fixed point in the UV that comes with a finite number of relevant directions, and it is really possible to follow the flow continuously from the UV towards the R at k equal to 0, and one gets exactly this type of effective action that has the dilaton term, Einstein-Hilbert term, and our infinitely many alpha prime corrections that are parameterized by this function. It is actually not so complicated. It involves logarithms and hyperbolic tangents. So I don't have time to go into the details, but we also tried to extend this solution to d equal to 4. I mean, in order to do that properly, one should resum the epsilon expansion. That is, of course, difficult, but we tried within some approximation, and it seems that it does not extend nicely to d equal to 4. Seems like there is a critical dimension that really creates that separates completely the UV fixed point for around 2 space-time dimension and the 4 dimensions between 3 and 4. So I will skip that details. So what I have shown you so far is that we found 2 solutions. So one is non-analytic, and the other one is an analytic solution that we have computed to leading order in epsilon via 2 plus epsilon expansion, and we have it in a closed form. And now, once one has the effective action, one can just use it to determine effective field equations to all order in alpha prime on cosmological backgrounds, no string loops involved, and check for the existence of de Sitter solutions within this setting. These are the effective field equations, but in both cases there are no de Sitter solutions compatibly with the implications of the swampland conjectures. And the reason is that in the one case, in order to have a de Sitter solution, one would essentially need this parameter C tilde to be 0. But this would essentially remove completely the gravitational part from the action. And on the other hand, in the 2 plus epsilon dimension, one would need the L function that appears in the effective action to be constant at the value of the Hubble constant, realizing the de Sitter solution. But we know that this function is not constant. And this leads me to my conclusions. So the existence of de Sitter solutions in the context of string theory is a big deal. It is an outstanding open questions. And it seems that within perturbative using the standard techniques and to the first few orders in the alpha prime expansion, there are no de Sitter solutions. So in this work we wanted to see if using some non-trivial, non-standard methods, it would have been possible to resum alpha prime corrections and start exploring non-perturbative aspects of the string theory, at least on cosmological backgrounds, and try to see if one could find any de Sitter solution. And within mini superspace approximation, bosonic string, and no string loop corrections included, we were able to resum all alpha prime corrections using functional normalization group techniques. And we found 2 solutions, one non-analytic, but exact in principle and valid in any space-time dimension, and another analytic solution via a 2 plus epsilon expansion to leading order in epsilon. But it seems that at least within approximation, this solution does not extend continuously to the case of d equal to 4. We have investigated the resulting effective field equations, but we did not find any. We found that the de Sitter solutions are essentially incompatible with these solutions. And of course, there might be other solutions because the questions are non-linear, but we were not able to find other solutions. Yeah, and as an outlook, we will continue in this direction, also trying to explore critical cases in other dimensions, and also on we will try to do the same on general backgrounds in order to compute some higher derivative corrections to Einstein equations. Okay, and with this, I thank you for your attention and looking forward to your question.
Thank you, Alesia, for this interesting talk. There's a question by Daniele.
Yes, thanks for the nice talk. I was wondering, what should we expect about the reliability of this FRG analysis when we go beyond the mini superspace? Do we have examples from similar analysis for different years that is first done in a mini superspace type approximation, and then we extend it? Are the results obtained at the mini superspace level reliable, or do you expect them to be drastically modified?
A good question. I don't think I have a good answer. So, for instance, even in the case of loop quantum gravity, so loop quantum cosmology in a sense follows a similar is motivated similarly. One just start from mini superspace and try to quantize the theory in that way, but there is no, to my knowledge, no guarantee that one would.
I meant in the FRG context.
In the FRG context,
studied by FRG methods, first in a mini superspace or similar type of symmetry-reduced approximation, and then extended.
Okay, so there, I know I'm aware of only one work by Daniel Littim, who studied the functional normalization group equations in mini superspace, and he obtained still the existence of a fixed point, but a flow that was different from, especially in the IR. I remember it was different from the standard one, but I'm not sure one can really compare the two cases, because in that case it was an approximation, it was a truncation, Einstein-Hilbert, and that's it. In this case, we had a function of h squared, so we had all possible corrections, so I'm not sure how to compare these two cases.
Hi, I missed, or I did not understand how you got away from the 10 dimensions of string theory to the lower dimensions. Did you do some compactification, or?
No, just not. I did not start from 10 dimension. I left the arbitrary. And the reason is that when one imposes the while anomaly cancellation, in principle, the result that D has to be 10 or 1026 comes from the first order result and on flat space times. But in principle, there are infinitely many corrections, and one could still accommodate D equal to 4 if the while anomaly cancellation can be realized with infinitely many derivatives, right? And so we left here the arbitrary and computed corrections independently, essentially, of the dimension. So for any dimension, at least the beta functions are hold for any dimension, and then we specialized to some cases to make the computation doable, at least for the analytic solution.
You're saying that these lower dimensional things are consistent string backgrounds for critical string?
I think so, yes.
Okay, interesting, thanks.
Related to what Harold was asking. So in this analysis, there is no specific input about any kind of string theory per se, right? I mean, if I take different string theories, I would still write the same equations. Is that right?
So I think I did not really get the question. So whether it is really string theory, I mean, the starting point is string theory in the sense that we use this effective action that has been computed by, at least the general form, okay. Has been computed by in various steps. First, some inputs came from this paper by Meissner. I can send it to you. I did not really write the details of the paper, but and then it was restudied more recently in 2015 by Holm Zuibach in a series of papers who proceeded with this in this direction and put further constraints, arriving at this very nice form for the effective action. And the ingredients that come in are those that I wrote here. So it is essentially imposing the Weil anomaly cancellation, integrating all massive modes, restricting to cosmological backgrounds, and the cosmological backgrounds in this context means mini superspace plus the B field set to 0, and T-duality. And this is enough to arrive at this equation. And this was the starting point for applying the techniques that I've discussed afterwards.
Thank you.
I have a quick question.
Yes.
I missed the step between the flow equation and the action. You must have integrated the flow equation starting from initial condition. What was the initial condition?
Okay, so the initial condition is a big issue, especially if one wants to integrate the flow numerically. But as for the analytic, non-analytic solution, one can check that this is just the a solution. Well, this is a particular solution of the flow that one can see that it solves the equation essentially just by looking at them. While for the
sorry, but it still contains some k, and you want to let k goes to 0, right? So you just set k to 0. Is that what you do?
So yes, in principle yes, but here I did not do that because in any case this solution is not really nice to analyze. But in this case, yes. So this is the solution at k equal to 0, coming from the most general solution to the flow in 2 plus epsilon dimension. Is really the general solution that one obtains by starting from the fixed point and perturbing it.
So there is an assumption about some fixed point start.
Yes. So in this case, yes, we assume that there is a fixed point, or I mean, in this case, there is a fixed point. We can see it, but we need to use that as an initial condition. Otherwise, one would not be able to compute an effective action that depends on a finite number of parameters.
Okay, thank you very much. Let's thank Alesia again. And the next talk is remote.
Can you hear me and see my screen?
Yes, we can. So next speaker is Arthur Hebecker, and he will talk about the recent issues in the quest for stringy de Sitter models.
Let me see whether I can make it full screen. Oh, what am I doing wrong here?
Sometimes Control L. Yeah.
Oh, okay. Thank you. No, not on a Mac. The problem is that some other panel, which I didn't see before, blocks the place where I can make it full screen.
Yeah.
Oh, wait, now I think I found a way.
It's okay. I will warn you 5 minutes before the end time of your talk.
Oh, okay. Okay, sorry. I'm struggling with. I apologize. I'm terribly sorry. I totally lost control of my Acrobat for some reason now. Let me try again. Was that successful, full screen?
I don't think so, but it doesn't matter. I think it's we can read very well even so.
Wait a second, maybe let me try again. If I stop sharing again. Still not full screen?
And now it's full screen, yes.
Now it's full screen. Okay, I apologize. It's each time it's different. Okay, good. So thank you very much. I'm very happy to be here. Thank you for your invitation. And I sincerely apologize for not having come in person. So my plan is as follows. So I will review some recent issues, and it will mostly be really review of de Sitter constructions, because I think there are very few people in this conference who actually work on this. And I'm open to questions. Also, please interrupt me during the talk. And there will be some recent original work as with the co-authors that you see here, but mostly will be review. So the outline is as follows. I will say something about the difficulty of realizing de Sitter in string theory. And I will report on progress in understanding of some of the issues. Progress in the 10D understanding of the brain geno condensation. You will see this is a key ingredient. And a new problem, which I will call the singular bulk problem of KKRT, which is one of the leading candidates. And I will explain why quintessence, which is sometimes discussed as an easy way out, is in fact not at all such an easy way. Right, so let me start here. So it is difficult to construct explicit de Sitter models in string theory. We have heard about the statement about already in the previous talk, and there have also been some long-standing, more general problems or discussions about maybe the impossibility or difficulty of realizing de Sitter in quantum gravity in general. I listed some authors. Alessia's talk was an example to make such a general argument. More recently, there have been concrete formulations of varying strength in the context of the swampland program, such that the V prime over V or V double prime over V conjecture. And I have also been part of this discussion, in fact, giving some critical remarks that some of these conjectures may be too strong, or the proofs, the so-called proofs have been maybe have problems. But it's certainly interesting to consider such arguments. And in fact, I will explain in a moment why such a very strong argument about, you see this potential here being very steep is not at all outrageous. So, but before I do so, let me recall the basic setting. In fact, I want this to be emphasized because it's really kind of sets me apart from the previous talk. It sets what I'm doing apart. It is a very different and I would say much more modest approach. The approach is to start with a string setting which we understand very well, 10D superstring in flat 10 dimensions with a coupling G string smaller than unity. In that case, it's, well, I don't accept it, widely believed that there's a very well understood 10D supergravity effective theory at low energies, the cutoff of which is a string scale MS, and which is smaller than the 10D Planck scale. So basically, the theory, if you raise energies, the theory is cut off by a transition into a so-called stringy regime when smooth 10D spacetime loses its meanings. And in this context, I simply see no way where I could have a running or a fixed point in a controlled way. You see, below the string scale, it's a standard EFT, in fact, infrared free, as gravity is in 10 dimensions. And at the string scale, spacetime changes entirely. So I don't see again how I could hope for a CFT-like fixed point in that regime. Anyway, that's my model setting. And now from that setting, I know that there are high dimension operators, of course, suppressed by the cutoff scale, and they are due to the stringy UV completion, and I know them explicitly. And they are as far as they are known, they are subdominant. Of course, we don't know all the orders. And then this gives rise to the possibility of a controlled compactification to 4 dimensions on a Calabi-Yau threefold. And this is all supposed to be in the regime of 10D supergravity as a low energy effective theory and controlled due to this. Okay, this is a very much more modest setting than what we had before. Good. So now, why are there in the setting problems with getting de Sitter compactifications? And there are many reasons. And let me give you one simple reason, which I think can be understood easily by someone not having worked in this field. So the generic result of a compactification with volume V, so V is the volume of the Calabi-Yau, and with some positive energy source in the compact space is given here. Namely, after compactifying, I get still the Einstein-Hilbert term, which comes from the 10D Einstein-Hilbert term, and the prefactor is the volume, simply because you integrate over the volume. Then the volume appears itself as a scalar field. It's a modulus, and it happens to have this logarithmic type of derivative term. And then there's some energy, which at the moment I don't specify. I just add some energy as a possibility in my extra dimensions. And even with this kind of very crude assumption, even letting this energy being positive, I see a problem. The problem rises as follows. Take this action, or this Lagrangian, and do a Weiro scaling, such that I can go to the Einstein frame in 4 dimensions. And the canonical field for the volume is phi, is a logarithm of the volume. And what one finds is a very simple Lagrangian, Einstein-Hilbert, of course, by definition, kinetic term for the modulus. And then, crucially, this energy term gets multiplied by e to the minus phi. So there's a runaway. And the exponent here is usually order 1. So simplest modifications due to this multiplicative term, even if the energy is positive, lead to a runaway behavior. The potential is simply too steep. Or in general, it's a steep falling exponential. Okay, so now one needs to go further. This is clearly too simple, and one can combine 2 such runaway potentials with different signs. But that allows only for ADS solutions. And you can see that very easily in this left picture here. So you have 2 such exponential lines. And if you add them, you can arrange coefficients such as there's a minimum, but the minimum will always be at negative energy. You could change signs and have a maximum at positive energy, but you can never have a minimum positive energy, which would correspond to de Sitter. This is simply due to functional analysis of functions, but clearly there's a way out, namely if you add a third term. So if you have 3 terms with different fall-off and appropriate coefficients, then you are able to get de Sitter. Then you basically take this term and this is called an uplift, you add another weakly falling term, and then you can create a curve like this with a maximum positive energy. But if all parameters involved are order 1, this can never happen in parametric control. So you will always have to rely on some parameter being accidentally small or large or some tuning. So now, sorry, let me see. So with some tuning, however, such parameters can be small and large, and this can be realized in the so-called string theory flux landscape. And I will discuss this now in some detail. So the earliest such scenario for realizing de Sitter is KKRT, and an important extension, which I will unfortunately not discuss, although it's very important, is the large volume scenario. So I will discuss an aspect of KKRT, which is also present in the LBS. So in fact, a large part of my discussion applies to both. So I will first recall how KKRT works and discuss a recent criticism, which was historically important, in fact, in triggering the debate about de Sitter and string theory that Alesia was referring to. And then I will come to a different concern, which in fact I would argue will threaten KKRT more seriously than the previous issue. So, but before these details, let me start with reviewing KKRT. So again, I remind you how modest my setting is, right? It's 10D supergravity, well-controlled, compactified on a large Calabi-Yau. For simplicity, I will take the Calabi-Yau to have only one modulus, one Kähler modulus, and so on. So, okay, so let's start. So we have a Calabi-Yau. Calabi-Yaus of complex structure or shape and Kähler moduli, and the complex structure moduli are fixed by fluxes. Expectation values of 3 form fields in the bound. Let me, even though not everybody may know that, let me assume this is something given and well understood. The only field left is the so-called Killer modulus, which is basically the volume. It's the complexification of the volume. The real part of this field T is the volume to the power 2/3. And we are here in the setting of supergravity. In fact, n equals 1 supergravity because it's actually Calabi-Yau identifold, but these are details that you don't need at the moment to follow. So there's a Kähler potential and a superpotential. Just n equals 1 supergravity, they are known, they're classically calculable. The Kähler potential has this form, -3 log T plus T bar. The superpotential is a constant after I have fixed the complex structure moduli. I mean, these two things are related. Once the complex structure moduli are fixed, this W as a constant is created. Now one applies standard supergravity formula to get the scalar potential, and it is written down here. So it's basically F term squared as in Ricci-Susi minus 3W squared for supergravity. The F term squared is given by the covariant derivative of the superpotential. Here's the inverse Kähler metric derived from the Kähler potential above. This is a covariant derivative. I've tried to be fairly explicit, assuming that many of you, of course, know supergravity. For the specific K and W given above, it turns out the potential is exactly 0. This is the famous no-scale form. And so far what we have achieved is very simple. There's a leading order analysis, complex structure moduli stabilized by W, and the cosmological constant is exactly vanishing, and one modulus, capital T, was a volume, is left completely undetermined. So it's a flat direction. And this is before many corrections which have to be added. So next step. 2 additional effects are needed to bring this to what is called KKRT. So the first is to stabilize T at positive vacuum energy. The first is to stabilize T at negative vacuum energy. So 2 additional effects are needed to get to positive energy, but the first effect only gives us negative. So the first effect is the geno condensation on a D7 brane stack. So this is a cartoon. There's the Calabi-Yau, there's a D7 brane wrapped on a cycle. This gives an additional term e to the minus t, just a SUSY version of confinement, and this is a well-established story. So now, at least in 4 dimensions. So now, in addition to this, it is needed to introduce an antibrane in a so-called warped throat. So the effect is adding a positive term which decays at large energy, and the origin, technically, is that the Calabi-Yau, due to the fluxes, has a so-called throat region. Strongly warped means basically there's a strong redshift in this region. Energy densities are scaled down. An anti-brane breaking supersymmetry in that regime will allow you, in principle, to uplift the solution to add positive energy density. Let me show this in pictures. Oh, sorry, my screen somehow has problems. Okay, here. As I explained, first we have the horizontal line. The geno condensation adds this potential. I will explain in more detail how it arises. In fact, it comes from the square of the e to the minus t term here. Let me go back. This expression here arises in the supergravity Lagrangian squared, and so there's an e to the minus t squared and linear, and this is responsible for this falling and rising curve. And then the uplift, the antibrane, brings us up. Here I drew to 0, but could also bring us up to slightly positive values. And there has been a long debate about this antibrane uplift, which I think has ended in favor of the sitter, but let me not go into this. What I want to focus now is a recent criticism of this setting, which led, I think, to interesting further work. And this is where I will try to give you a flavor about the present ongoing debate. A recent criticism was rooted in a possibly too simplistic treatment of what I called D7 brane geno condensate, and more particularly D7 geno bulk coupling. So let me explain that, of course, you understand that what I wrote down are simple effective formulae in 4D supergravity, and they got to have a 10D origin. And the 10D origin of these formulae is the flux. This stands for the term W. This is just energy density in the complex space, free-form flux. And then this flux has to couple to the geno bilinear on the brain. Omega-3 is a holomorphic 3 form of the Calabi-Yau. Delta D7 is a delta function localizing us to the D7 brain, a submanifold of your Calabi-Yau. So far this is known. And this explains part of the results of the 4D effective supergravity. But what has been observed and noted is that this is clearly problematic. Namely, if you try to start from here, not trust 4D supergravity, but simply integrate out G3, what happens is, because of this singular term here, G3 gets singular. And then you plug in the singular G3 into the square term, and you get a completely singular expression. You get a divergent effect of type delta function squared, right? Simple classical field theory. You have this expression here, you solve for G3, you plug it back in, basically integrating out G3, and your things blows up in your face due to a delta function squared. And then you can regularize, basically anything can happen if you don't have clear ideas what to do. And so this is where our work started a few years ago, and I will come at the end where to where we arrived. And the first thing to notice is that such singular geno effects have in fact been observed before, in fact very long ago, by Rojava and Witten in the context of genos living at the boundary of 11-dimensional M theory. And it has been shown that highly singular lambda squared terms save the day by completing the square. Basically, you need to have a quartic term introduced, the counter term, to compensate the divergence. And applied to our case, now I'm jumping ahead very fast, the correct Lagrangian is this one, not the one I had before. This Lagrangian, this is now our proposal, this Lagrangian includes a G3 squared, which is known to be there very well, a G3 coupled to the geno bilinear, just the mixed term of the square, and then of course also delta function squared, which you add at tree level as a divergent counter term. So very roughly speaking, what now happens is you integrate out G3. G3 has a flux part. This is the thing you add in by hand as a topological feature, and a dynamical part. And when you integrate out the dynamical part, the second term cancels most of the delta function. A finite remainder is left, and what you find explicitly is G3 flux plus lambda squared, all squared, and that reproduces the 4D supergravity result. And here on this slide, I actually plan to, maybe let me go through it very quickly. I'll just show you the analogs. These are formulae taken literally from Rojava. So exactly the same story. It's kind of an authority argument, right? It's a well-known story. There's a 4-form flux in that case. The 4-form flux couples to the geno condensate here. In this case, not on the 7 brain, but on the 10-dimensional boundary. And it's known that this proposal here works. Such a complex, and we basically, our proposal is to do the analogous thing for the geno condensate on the type 2B 7 brain. Okay, so let me now, here. So the most recent part of our work on this, which we were not able to achieve so far, and other groups were not able to achieve this, is to realize this the story in terms of an explicitly local and covariant action in 10D plus the 7 brain. So far, there were always some non-localities, some ad hoc assumptions left in implementing this complete square proposal. But now we have an explicit Lagrangian. It is so G squared always there, the flux kinetic term. This is the also known 10D, 7D version of the coupling, how the flux in 10D couples to the brain. The integral here is over sigma. Sigma is my brain submanifold. And then there are two things to be added. The claim is that the full proper type 2B action has to include a counter term, this delta function on the brain. So it's like a delta function squared, it's divergent. And a finite piece, which involves derivatives in a very particular way and is sensitive to the curvature of the brain. And what now happens is that if you start from this action and you integrate out the 3-form flux, then a divergent term arises. This divergent term is precisely cancelled by this second line. And roughly speaking, there are finite terms left now from the first two lines and the additional third line. And this conspires to give you precisely the correct supergravity formula. And so consistent with what people thought they always knew. And the quartic terms that are added are in fact the explicit microscopic origin of the e to the minus t squared piece in V, which was crucial in getting KKRT to work.
Arthur, you have 5 minutes.
Okay. So while this strengthens the LBS and one part of the KKRT proposal, I will now turn to a different problem, an issue that KKRT may have. I showed here recent work by other groups on the same story, which I will not, I mean, this is for your reference. And the new problem is the following. There exists, in fact, a parametric problem fitting the throat, this strongly warped region, in the Calabi-Yau. I will call this a throat gluing problem. One can understand in principle as follows. Namely, here is the actual metric. The metric is in fact not a Calabi-Yau, it's a so-called warped Calabi-Yau. There's a warp factor, y is a point, parameterizes the point of the Calabi-Yau, which multiplies the 4D part and also the Calabi-Yau part. And so it turns out that to get into the regime where the uplift works and the vacuum better stable, you need to make the throat. I drew it here in a rather ugly way. Here's the Calabi-Yau, very large. In fact, it turns out you need to make the throat bigger than the Calabi-Yau smaller than the throat. Now, these are all moduli. You can in principle do that. And you arrive at this very bizarre picture where you have some Calabi-Yau geometry connected to a throat, which is much thicker. This is unusual. This is maybe unintuitive, but so far nothing wrong. And so our claim is that the throat gluing problem, which is in itself not deadly, it entails, however, a so-called singular bulk problem. And that may destroy the full framework. Namely, this function h, the so-called warp factor, is known to behave singularly at branes and O-planes, which are the objects which carry opposite charge in that model. It blows up at the branes and goes negative at the O-planes. And since at the point where it goes negative, basically the metric becomes singular. You can see that if you remember the previous slide, h was multiplying the Calabi-Yau metric. So it shouldn't go to 0. And normally this is not a problem, because normally the picture is that you have this Calabi-Yau, you have some very small singular region around the O-plane. In that regime, we trust the stringy resolution. We don't trust the 10D geometry. But what we find is in the Calabi-Yau regime, due to the throat gluing problem, you're forced into a situation when a large part of the Calabi-Yau disappears behind the singularity, which is severe, which really restricts your control. Let me, sorry, I was jumping too far. I have here one slide explaining this. Maybe, I don't know whether I should skip it. Let me skip it. There's a slide here arguing analytically why in the parametric control situation of KKRT, this function, which I'd call h here, needs to have a large negative region where you lose control. But this is probably in the time is running, and it's probably not reasonable to try to explain that. So I leave that to you to read the papers or just read up on the slides. Let me go on. So it is conceivable that all the constructions will fail in the end. I am by far not convinced of that, just because KKRT has this problem. The other issue with geno condensation was overcome, I think. LVS is an extension of KKRT which does not have the singularity problem. So there may be other problems there, but I think at the moment we are still in reasonably good shape. Nevertheless, we have to be serious about the possibility that all these constructions could fail. And then it has been claimed that quintessence is a natural way out. And the last point I want to make in this talk, and I think this is my next to last slide, is that quintessence is not at all such an easy way out. So it is, because it faces what we call the F-term problem. So let me first recall what quintessence is. Quintessence means that you don't impose a cosmological constant, even though we appear to see one. Instead, you have a very slowly rolling light scalar field, and in the far distant future, the energy will go to 0. And there's no problem if you fundamentally forbid the sitter. But the field has to roll very slowly, it has to be very light to describe our present cosmological data. So in this quintessence field, this very light field, in the best understood cases, it has to be a Kähler modulus. Nobody else in this type of models is that light. And for this, to keep this Kähler modulus, or this volume modulus, well, it's not an actual volume modulus. It's a modulus of a ratio of 2 4 cycles. Let me not go into details. To make this modulus extremely light, you need an extremely large volume. And now the following story happens. We know phenomenologically from the LHC, the supersymmetry is broken at a fairly high scale. Sorry. So there is this F term squared from our observed SUSY breaking. Unavoidable, because we simply know there are no superpartners, the Gretino is not seen, and so on. This turns out to be much bigger than the whole supergravity effective potential, scalar potential, which you derive using the Calabi-Yau setting I described before. So something completely new has to happen. Some new scalar potential term is needed. And so, in fact, realizing quintessence runs into problems which I think at the moment, maybe in the future this will be overcome, but at the moment they are harder than getting some version of KKRT or LBS to work, the issue I explained before. So that already brings me to my conclusion. So I think we agreed between Alesia and my talk that establishing or disproving stringy de Sitter is a key goal. And the intention here was to provide only a flavor of the challenges for those who work at the positive side, the technical level, to get this to work. Maybe also see why concrete proposals do not work. Let me emphasize at this point that I agree with Alesia that purely perturbative constructions appear to fail. But what KKRT and LBS is a very tricky thing using a non-perturbative effect, which you control in 4 dimensions, namely the geno condensation, together with a perturbative treatment of 10D supergravity. And so this is how these things could work. And so this is formally satisfying the requirement, it should be non-perturbative, but is still largely controlled by perturbative stringy calculations. That is an important point, I think. So being non-perturbative does not mean uncalculable. So now, so my first point was KKRT appears to survive the recent 10D line of attack. And I think it is a very interesting result because it basically tells you how to extend the 10D supergravity action, the famous time to be action, by a crucial term, right? A new term, which is not maybe established due to our paper, but is there's a suggestion out there which needs to be checked and verified. So nevertheless, KKRT may fall victim to what I call the singular bulk problem. The LBS large volume scenario does not suffer from this latter issue, but it needs a further ingredient, alpha prime correction. So it is a slightly more involved setting, which I apologize was no time to discuss. And I also emphasize that in parallel to proving or disproving KKRT or LBS or others, one should try stringy quintessence to work. And as I argued, that is maybe a way out, but not a cheap way out. Thank you very much. That's all.
Thank you. Are
Yes,
there any questions?
Can you hear me? I'm ready to
Here in the audience.
Hi, thanks very much for the talk. I have a very naive question. Are these problems that you discussed, are they more relevant in the context of inflation or late time acceleration or both?
I think they are relevant to both, because in both cases, you essentially need to stabilize moduli. I mean, also in inflation, you need to do that in the presence of a large vacuum energy. I mean, the scales are different, but I believe that usually inflation is something that people build on top of stabilized moduli. I mean, there are other suggestions, but the most standard suggestions use modular stabilization first. And so I think they are really relevant to both questions.
Okay, yeah. So sort of as far as the late time acceleration is concerned, since we are sort of not so, the universe is not so terribly old from that point of view, isn't it? I don't know. Some naively, I would have thought maybe, you know, it could be quite metastable. I don't know. So my question is: are these more serious in the inflationary scenarios, or what's the attitude?
My attitude is that we know less about inflation, and so I'm less concerned about inflation. Even though I think I'm very much on the side of inflation being a part of our present worldview. I'm not in any way, you know, neglecting the importance, but I think our universe today is even more relevant. And let me say that the smallness of the energy density that we see today, which maybe makes you think the problem is not as hard, that is exactly, I think, a misconception related to my previous slide here. Let me show this slide. You can still see my slides, right? Can you?
Yes.
Yes. So you see, you have this huge F term in addition to the supergravity result, which you simply know phenomenologically. So basically, even though we have zero in our total sum of terms, the zero arises between a large positive term due to SUSY breaking and some negative term, which we don't know. And so the fact that we see a total almost zero does not make things much better. We still have a high SUSY breaking scale and a high contribution to cosmological constant from a large F term energy or whatever positive energy, which we simply know because supersymmetry is broken. That's the reason why quintessence is not an easy way out. Otherwise, you could say, you let your fields roll to large values, and in the end, everything will decay. You go to supersymmetric flat world, and that may be fine. But it's not fine because we know supersymmetry is broken very strongly right now, and it doesn't go together with a very slowly rolling scalar, which is just unstabilized.
Okay, thank you.
Please stay. You can ask. Maybe I was too confusing. Ask something simple, please.
So I don't see any further questions, so we thank Arthur again. And
thank you very much. Thank you.
Next speaker is Maja Buric.
Hello.
No.
Did I share screen? No, not yet. Okay.
Yes.
And now?
Yes. Perfect.
So
good.
Okay.
So Maja will talk about fuzzy de Sitter and anti-de Sitter spaces.
Okay. So my talk is basically a talk on non-commutative geometry. So it's not. It doesn't explain anything like a model of, I don't know, like a string theory model or anything, except that non-commutative geometry and operators or objects which arise there and which are basic can be, of course, assumed to be fundamental in some sense, but also effective. So if we have some background or basic fundamental theory based on some basic fields or ingredients which are quantized, then if space-time emerges, coordinates or momenta or whatever could be some effective combinations of these fields. And in this sense, non-commutative geometry could be looked upon as an effective theory as well. The other question is whether we would expect from effective theory to have some geometric structure, but perhaps at least because of the classical limit or commutative limit to Riemannian geometry, one might expect intermediate steps to have also a geometric structure. So I will say a couple of words about this formalism and then give you some results which we obtained previously about the Sitter space in 4 dimensions and some initial work which is done at the moment about anti-de Sitter in 3 dimensions. So in this frame formalism, I mean, there are many details, but what I wanted to start with that we somehow select or single a set of coordinates and a set of momenta, and the structure is made in analogy with the commutative or Cartan frame formalism. So coordinates somehow define the basic geometric structure of space-time. And so in the commutative space, you can speak about range of variables, which defines boundaries, then about singular points, usually one assumes that manifolds are continuous and that you have diffeomorphism symmetry, so you can have changes of coordinates. And then in order to introduce some differential geometric structure, in commutative case, one can introduce partial derivatives or frame derivations, E. And typically on manifolds, a unique differential calculus is the RAM differential calculus. So one can build one forms, two forms, and so on to, to define fields, gauge fields, I don't know, scalars, spinors, and so on. In some way, one can say that gravity is incorporated in the intersection between momenta and coordinates, in the sense that the tetrad field is a frame derivation of coordinates. And in the non-commutative case, this frame derivation or any derivation is typically or in general realized through a commutator. Then from a tetrad or a Filbine, you can get a metric and so on. Okay, in this non-commutative generalization, which I'm talking of and which is based on John Mador's frame formalism, it's made in such a way that the space-time can be either a curved commutative space, or it can be the algebra of functions, either of either operators or matrices. So it's made very generally. I will denote this non-commutative space-time by E. And the fact is that derivations or something which was outside of the space-time in commutative space, that is partial derivations, now can be inside. But this implies, or in some sense implies, that differential calculus is not really uniquely defined, and this is a kind of a problem. A further thing is that the space of vector fields is infinite dimensional, because you cannot just multiply by function. Well, when you multiply vector field by a function, you essentially obtain a new vector field linearly independent. So therefore, tangent and cotangent spaces do not have fixed or finite, and one has to define them basically. And one way to do it is to restrict a tangent space, or to restrict the number of derivations, for example, like to some natural set of frame derivations which are given by geometry which you want to achieve. Or okay, so this calculus has a lot of good examples. One of them is the fuzzy sphere, and since we defined the fuzzy de Sitter in analogy with the fuzzy sphere, I wanted to add that this idea, it contains the idea that you can do the embedding through the Casimir relation if you are in some kind of, I don't know, if you have some symmetry, like if you're in the Lie algebra or Lie group. And this somehow works very nicely and effectively for the fuzzy sphere. So our motivation to do this work was to produce some realistic examples in 4 dimensions, or in 4 dimensions. But then, first of all, since fuzzy sphere is based on symmetry, it seems easy, or maybe the best thing to start with the spaces of maximal symmetry and to try to quantize de Sitter or anti-de Sitter spaces. And then to check whether there is anything we can say about cosmology on these non-commutative spaces, for example, and at all, whether we can obtain realistic physical results, whether we can obtain commutative limit, whether we can obtain some new phenomena. particular thing is how could one describe, for example, singularities or boundaries, or if we would talk about black holes, horizons and so on. And a particular problem in this is when you want to deal with non-compact spaces, you have infinite dimensional unitary reducible representations. And you have more complicated algebra, so whether one can deal with these problems and how. So the first thing which I want to describe is fuzzy de Sitter space in 4 dimensions, and this is based on the use of the de Sitter group or correspondingly algebra, which apart from 10 generator has quadratic combinations, which are generalizations of Pauli-Lubanski, and which are kind of natural candidate for vectors or for embedding, which give the embedding, because this group has 2 Casimir operators, quadratic one and the one of the 4th order here. So therefore, if we proclaim that coordinates in some 5-dimensional space are given like this, are proportional to W's, then this Casimir relation could be analogously to the fuzzy sphere, for example, be interpreted as the embedding in of the Sitter space in 5 dimensions. And there you can relate the cosmological constant with the Casimir Casimir invariant of the group. And here it is some length scale is introduced, which would characterize a non-commutativity scale or the Planck scale or something like that. So a natural or perhaps natural idea is, or definition is to say that fuzzy de Sitter is a unitary irreducible representation of the Sitter group. So now there are several classes or series of unitary irreducible representations, but of course they are all infinite dimensional because the group is non-compact. It seemed to us that it's the most natural to work with the principal continuous series. And the reason probably was technical. That is the first, we first came to Hilbert space representations of the principal continuous series. Of course, discrete series also is interesting, because in discrete series you would immediately have, for example, discrete cosmological constant and perhaps some different physical conclusions. Except for coordinates, one would want to have momenta to speak of differential geometry, and this is the choice of this momenta. There is the whole machinery of differential geometry, which I skip, of course. If you have a fixed momentum operators, then you can discuss connection and curvature and the line element. And for this choice of momenta, the line element which you get from non-commutativity naturally is the Sitter form of metric with flat sections. And then furthermore, you have from it that the cosmic time is logarithm of this combination of previously introduced operators. And one can identify also the conformal time. But this choice breaks the symmetry, so this non-commutative space won't have the full de Sitter symmetry because we reduce somehow the group, but we have Friedman-Robertson-Walker type of metric. And then I roughly go through some results. One can introduce differential geometry. One can calculate the curvature. The Ricci tensor, for example, is not exactly like in the usual case. I mean, in this case, it is not, the factors are different here, but the scalar curvature is constant. And one can talk about Laplacian, that this is what is the topic, so to say, because we wanted to see whether it's possible to define scalar field and Klein-Gordon equations and so on. This non-commutative geometry in this case gives us, if applied directly, the Laplacian which is not Hermitian. This can be seen with the Laplacian with the form acting on functions, and analogous form is when you act on wave functions or vectors in the representation space. So what we did is we symmetrized this operator, this Laplacian, and we ended up with a kind of familiar expression, quadratic in the generators of translations or in momenta. And the idea was to try to find the spectrum of this Laplacian and the eigenfunctions to see how one could quantize the scalar field. Okay, these are some slides on the representation. There is a in the representation which we used, which seems apparently reducible, but essentially it is not. But that's probably I will skip this. It brought us to some confusion in calculations. But anyway, one can discuss how the coordinates and energy Laplacian look like. And the results are as follows. So spatial coordinates look as in the normal commutative case, their spectrum is continuous. This initial embedding time, which we started from, which is a 5-dimensional, so to say, observable, it is discrete, but cosmic and conformal time again continuous. So the space-time looks very much as viewed from the aspect of the spectrum of coordinates, very much like the ordinary de Sitter space. We try to calculate to estimate the radius of the universe, which can be defined as normal, hoping or expecting that somehow non-commutativity will hide the singularity, forbid the singularity r equals to 0. But unfortunately, it is not true. If we restrict to half of the space, which would correspond to one particle excitations in some scalar field theory, then we would have that the expectation value of the radius is strictly positive, or that it's bounded by the value of the Casimir operator. But in general, it is not. So one can identify what is the energy. So it is one of the generators, dilation, and it commutes nicely with the cosmic time. This one can also solve for this and eigenvalue problem, and the energy has the continuous spectrum. So basically, we wanted to discuss the Klein-Gordon equation or the eigenvalue equation of the Laplace. And now I will show you a little bit of the result. So this can be done. I mean, in all these calculations, since we are doing always spherically symmetric operators, one can divide one can do basically the radial equation, which is of this type. So solution to this equation is given by the hypergeometric function. And this was a little bit unfortunate because these functions, okay, spherical harmonics we can deal with, but these functions are a little bit difficult if we want to expand any field in hypergeometric functions. I don't know. I mean, Bessel functions or polynomials would be much better. So this spectrum is continuous. One can analyze the functions, but what is interesting is that for each mass, if we solve the Klein-Gordon equation, basically the solution just depends on angular variables L and M. So we have a typical thing which is always true for in non-commutative cases, that the number of degrees of freedom reduces. So I have this comment that probably it were better if we used from the beginning conformal field theory representations of SO41. But then this representation which we used perhaps gives, this hasn't been analyzed in all details, but perhaps it gives the division of the Hilbert space of states in an equivalent of the positive energy states and negative energy states, which is necessary to discuss quantum mechanics or one particle states of scalar fields. So perhaps if we reduce to half of the space, then some more concrete conclusions could be drawn. And of course, discrete series might be with better results. Another model, which I will just mention briefly, is De Sitter in 3 dimensions. And the idea was to try to understand whether we can say something about BTZ black hole, which is quantized, so which is given by operators. And since this is, I mean, we did several or quite a lot of calculations, but somehow we haven't finished this. So since I cannot talk about concrete physical results at the moment, I will just give the initial things. So in analogy with previously said, the idea is to use the symmetry algebra of this space, and this is SO22 group and the correspondingly algebra. We can write it using these generators, but also perhaps it's easier and to work with to work with this property that this SO22 is in fact the tensor product of 2 SU2 So we used throughout the calculation this division, introducing these 2 types, so SO and SO bar, which have 3 generators, each of them. And of course, they commute mutually. The point with SO22 is that both or with Lorentz group SO31 is that both Casimir operators are quadratic. So one cannot introduce the trick like embedding, which is done for the fuzzy sphere or for fuzzy De Sitter. So one has to use reducible representations differently, and it's a little bit, for this reason, it's a little more difficult to obtain both quantization condition or the classical limit and things like that. So the Casimirs are given by this formula, and the representations are tensor products of the representations. So I can essentially speak of one of the factors. They are infinite dimensional, and again, we have all 3 kinds: principal, continuous, complement, and discrete series. And in this, we used or analyzed discrete series, which have also, I mean, all these have Hilbert space representations. For example, discrete series can be represented by holomorphic function in the upper complex plane, or by functions in the disk of radius 1. So this is Of course, every representation has its drawbacks and advantages when you start to calculate. And what the problem or the result which I will show you is how we solved this division in coordinates and momenta in such a way to obtain the metric of anti-de Sitter. The point is, of course, in which coordinates right anti-de Sitter space, since it is not obvious at all. But so what we chose is Poincaré coordinates because the line element somehow looks the simplest, or because all coordinates or these commutators and all tetrad components or feedback components depend just on one variable. So in fact, we should, within this algebra, seek for coordinates and momenta which satisfy these commutators. And we found a set of these, a set of solutions. Also, we wanted that momenta belong to the Lie algebra, because in the structure is simpler and somehow we have some remaining symmetry, and the differential calculus essentially simpler. So our momenta are like this, whereas coordinates are more complicated. They are not in the Lie algebra. They depend on the square roots of the generators. And this is, in fact, the other or the reason why we chose to work in the discrete series, because in discrete series, these E plus minus generators have their spectrum only either positive or negative. So we chose so one can define the square root. I mean, IA plus here is Hermitian, as I wrote the commutation relations with anti-Hermitian operators. So there is a nice set of coordinates now, and one can proceed to analyze how they behave and what do they give and so on. And this analysis is partly done, but not really fully. So I conclude with some general statements that, well, I think that this coordinate momentum duality, or this gives a good insight, even if not the full formalism is true, that one can understand what goes on and how to generalize the commutative into non-commutative manifolds or spacetimes. And a very useful tool is non-commutative frame formalism, because it guides you and tells you what objects are relevant in this way. Okay, that's it.
Thanks. So you have a question? You can ask it here.
Hi, Maja. This is Harold.
Yes.
Thanks a lot. I like very much the underlying construction. So, for example, consider the first part, the de Sitter space. But I think the construction that you use does not give you a de Sitter space, but it gives you a higher dimensional space, which is a bundle over the de Sitter space with a non-compact fiber. And there are several ways to see that. I mean, one is, if you consider the spectrum of the Laplacian, I mean, you have to work out the full space of functions, which is the endomorphism on a Hilbert space, and you will get functions, you will get Kaluza-Klein modes with even a continuous spectrum. Or from a geometric point of view, if you consider coherent states on some point, and then the stabilizer group is non-compact, this is a Lorentz group, and then gives you a non-compact orbit. So however you look at it, I think all these spaces have an internal space, is a bundle. And in the de Sitter cases, and also anti-de Sitter, it's non-compact. So that I would worry about that aspect. Have you thought about that?
No, I mean, I don't exactly know why. I mean, that would be a problem if you wanted to.
Well, I mean, if you want, for example, if you want to do field theory or gauge theory on sort of thing, you need, I mean, the spectrum of functions, all the modes are just all operators in your Hilbert space. So they're all functions, which means they describe functions on the entire bundle and not just functions on the zeta space. So it has more content.
Okay, probably, yes. Yes, but yes, I don't know. I mean, whether this is, in which sense this is an abstraction, I'm not sure. Well, this is not a problem. We had, of course, there are many problems, but at the moment we deal with computational problems of concrete representation. This would be probably interpretation problems, a kind of. But then the interpretation doesn't have to be the same as in the usual commutative case, no?
If I may, I ask also a question. In the ordinal geometry, it is often said that the Euclidean continuation of the zeta is a sphere. So is there any sense in which a fuzzy sphere is the Euclidean continuation of a fuzzy de Sitter?
Well, I don't know, perhaps it's possible, but the point is that when you go to, if you do the Euclidean continuation of a representation, or if you would like to change to multiply a specific some generators by I, then you would go from unitary to non-unitary representations. So in this sense, I mean, one might do that, but typically we would like that coordinates, for example, are Hermitian, so that it would, the answer is this would include in the whole discussion non-unitary representations. This might not be necessarily a bad thing, but one should just pay attention to this point. I mean, it's not so automatic. The Wick rotation is a kind of non-trivial, I think.
Okay, thank you very much. I don't see other questions, so thanks.
Here in the,
oh, there's one online, sorry.
Yes. I have a very, very kind of naive question. If you involve gravitational waves or gravitons, normally diffeomorphism invariance is very crucial to get the 2 degrees of freedom. I mean, to get the actual features of a gravitational wave or graviton that we know. Is there some sense in which something similar happens here? I mean, how do I see the diffeomorphism invariance, or how do we at all see the degrees of freedom, the right degrees of freedom of gravitons come out?
Yes, so this wasn't discussed really here, but the diffeomorphism invariance in this, I didn't speak about this formalism, but it is included, and then you can do gravitational waves like starting from some general, if consistent, background, and then doing the small perturbation, like in the WKB, and then, well, I don't know, it's maybe not obvious, but it is restricted. What is not present here is the local Lorentz invariance in this formalism, because somehow you have to break it by the choice of the frame. But the invariance a priori is reduces to the change of, I mean, you can...
Yeah, I understand, but where do I look for gravitational waves in this context? Can you give me a reference or a name or?
Mador did this as in perturbations on commutative backgrounds. This was a paper done in 2000, I don't know which, 6 or 10 or...
Thank you, thank you.
So in principle, it's possible to do perturbations that it has been done. Well, what has been done in more details are the perturbations of the flat space. So if you have non-commutative, then it's easiest because then the commutators are constants and then you can proceed further. But the result is not identical with the classical one. That's also for sure.
So at this point, we can thank Maja again. We have a break and we start again at 6 o'clock.